You can meticulously draft a pristine software architecture on paper, but diagrams do not actually execute in production. Code does. Defining pristine domain boundaries on a whiteboard offers no guarantee that the resulting implementation won't be difficult to read or modify. A useful domain model must minimize the intellectual load required to use it. Eric Evans calls this supple design. This concept has nothing to do with code golf. We aren't chasing the lowest line count or deploying clever syntactic tricks. Supple design means the code's behavior, its constraints, and its domain meaning are explicit in the interface and predictable in its execution. To see how this works in practice, we will deconstruct the financial logic of syndicated loan shares. The ultimate test of a domain model is whether an engineer can safely alter its implementation without the risk of breaking the system. Consider a baseline implementation for distributing these loan payments. Usually, it takes the form of a procedural script. An engineer reading this code has to mentally track nested for loops, multiple hash maps, and cascading conditional branches. Because the calculation relies on generic temporary variables, raw big decimals, the developer must hold the mutating state of the calculation in their own working memory. The actual financial formula is buried underneath the mechanics of data structures. To understand what the code is attempting to achieve, developers are forced to manually trace the execution paths line by line. When the business intent is completely indistinguishable from the execution steps, legacy systems become extremely brittle and difficult to modify. The first step out of this trap is adopting intention-revealing interfaces. Methods must be named for their domain result rather than their internal mechanisms. This UML diagram from the original DDD text illustrates a paint mixing model. The interface uses mixin to communicate a domain action, rather than exposing the underlying array manipulations required to combine the colors. Applied to our loan scenario, we replace the procedural calculation block with a single method named prorated distribution. Clear naming, however, cannot eliminate logical instability. The central danger of procedural code is that it mutates existing state, creating unpredictable side effects. We eliminate this risk using side effect-free functions, implemented through an immutable value object. If we encapsulate the financial data in a share_py object, operations on it do not alter the original. Instead, the method returns a new object containing the calculated result. Immutability makes calculations safe to combine. No operation can secretly corrupt another operation's data. Eliminating side effects shifts the developer's focus from tracking state changes to understanding the business outcome. The original procedural code also relied on implicit rules, assuming the developer knew that financial loan shares must always equal exactly 100%. We bring these hidden rules to the surface using assertions, explicit guard clauses placed directly inside the object. Making these constraints explicit means any calling code immediately understands the strict requirements of the model. This level of isolation creates a standalone class, a component that can be understood, tested, and reused completely in a vacuum. The share_py object achieves this because it knows nothing about database repositories, UI formatting, or application frameworks. Isolating self-verifying classes limits the intellectual load to the class itself, as engineers only need to understand the logic of that single unit. We can push this further with closure of operations, where an operation takes arguments of a specific type and returns an output of that same type. This closure enables math-like composition. Complex business rules can be chained safely, knowing the output format is always consistent. Applying these tactical patterns yields a state of declarative design. The code no longer reads like a procedural script dictating how to execute instructions. It reads like a declarative equation stating what should be true. Declarative code creates a design where the implementation reads exactly like the financial rule it represents. In a massive legacy monolith, applying supple design to the entire system is rarely possible. Architects need specific angles of attack. Focus on the modules that carry the highest business value and suffer from the most complexity. Within those modules, leverage established formalisms. If the domain relies on standard accounting or physics, adopt those mathematical rules directly instead of inventing custom abstractions. This rigor should be reserved for the core domain, where business complexity justifies the architectural effort. True supple design is distinct from fluent APIs that simply chain methods together for convenience. Fluent APIs often mutate state behind the scenes, creating the same unpredictable side effects Supple Design aims to eliminate. Avoid the instinct to create microscopic classes that add conceptual noise without increasing domain clarity. Fewer lines of code do not automatically yield a simpler or safer model. When names reveal intent and functions are side effect free, the implementation becomes a direct expression of the business rules. The developer stops fighting the code and starts solving the problem.